Race conditions are one of those bugs that makes you question your sanity. The code looks correct, the logic makes sense, it compiles, it even works sometimes. Hello world, I'm Nick, and in this video I'm going to be showing you two examples of race conditions in C#. We're going to look at how we can reproduce the race condition on demand and then how we can fix them properly. So if you're not quite sure what a race condition is, don't worry, because it's taken me a long time to really understand them. But race conditions are when multiple threads access a shared state. So you can think of it as one piece of data and then multiple different threads accessing it at the same time. That on its own isn't necessarily bad, but when the correctness of your program depends on timing, it becomes an issue. If two things happen to that shared data at the same time and you didn't explicitly control that, i.e. you didn't intend for that to happen, then congratulations, you've just created a race condition. So the first example, let's look at some C# code where multiple threads are incrementing a shared variable. The final value is one that can be predicted. It should be an expected value, but it's wrong. Let's take a look. Okay, so let's look at some broken code then. So we've got a console application here, and we've got, outside of our main method, a static integer. So we've got a static field with a value of 0 called counter. This is really important because this is the shared value that we're going to be incrementing, but we're going to be incrementing it from a number of different tasks. So here we have 10 tasks. When we start our console app, we go into our main method and we create 10 tasks. We're going to iterate over this array of tasks, and for each of those we're going to kick off the task and it's going to iterate the shared counter up to the value of 100,000. So if you think about each task, it has its job, there's one counter, and each task is going to say, increment that 100,000 times. And so 100,000 times 10 is 1,000,000. So mathematically, if these were working properly, we should end up with a result of 1,000,000 at the end. And so what we're doing here is awaiting all of those tasks. So we can say await task.whenAll, so when all of those tasks are finished, we'll have our final counter value, and then we're just going to do a console.write line, which will write it out to the console screen. Now, obviously, we know this is not going to work, but let's run it so that we can give you an idea of what this looks like. So if I run it once, I expect to see 1,000,000. What do we get on the screen? Let's just zoom that in. You can see their final counter value is 454,940, 454,940. Not 1,000,000. Doesn't take a mathematician to recognize that. If we run it again, maybe we get the same number. Nope. We get a completely different value, 638,909. So let's dig into why this is happening. This is a race condition. Okay, so now we're a bit more acquainted with what a race condition is. Let's figure out why this happens. So why does this happen? Well, it happens because this line, counter plus plus, is not one operation. Okay, it looks really simple on the screen, but under the hood, it's actually 3 steps. So the first step would be to read the value, the second would be to increment that value, and then the third would be to read it back. Now, imagine that 2 threads are reading the same value at the same time. They're both going to increment and they're both going to write the same result. One update disappears, not because the maths are broken or the math is broken if you're in the States, but because timing allowed that overlap. And this is called a lost update, and it's one of the most common concurrency bugs. So how do we fix it? Well, option 1 in C# is to use a lock. A lock says that only one thread may execute this section at a time. So if you don't know, to create a lock, we can create an object, and it looks like Copilot has already anticipated what I'm going to do. So we create a read-only object called lock, and we just new that up. And then what we can do with that is wrap the counter in this lock. So inside the loop, we can say lock, let's use the lock keyword, and then use that lock object as the lock object. Cut that and paste it into there. Now those 3 stages we talked about, the read, the increment, and the write, can happen without interruption. So let's run this. If I start the program, and now that we've put a lock around the counter, we should see 1,000,000, and we do. We see 1,000,000 there. Let's just run that again, just in case. We see 1,000,000 again. So we get a perfect result every time. The second option is to use something called interlocked. This performs the increment as an atomic operation. So atomic in this context means that that something is indivisible. The CPU will guarantee the update happens as one unbreakable action. So no thread can interrupt halfway through. So let's change what we've done here. We'll get rid of the lock. We don't need this object anymore. Tidy this up. And then what we can do, we can use the interlocked keyword. And interlocked has some simple built-in functionality that we can use whilst guaranteeing that these operations are atomic. So for us, we want to use the increment functionality, and then we add a ref, so it's referring to counter. So we can actually get rid of that. And instead, we're not using the plus plus anymore. We're incrementing it by using interlocked.increment on this counter object. So let's run that again. And you can see we have a result of 1 million. I'm just going to run it again, 1 million, one more time, 1 million. So even though we've got all these different threads running, all these different tasks running, we're getting the same result each time. And the good thing about interlocked is it's actually usually faster than locking. So use interlocked if you've got a simple numeric state, and use locks when you're protecting logic. If you've got more advanced logic, then you can use a lock for that over something more simple, numeric, interlocked. Okay, that was a simple example, but now let's look at a more realistic race condition. And this one is a bit more subtle. So here we're checking if an item exists before we add it to a shared collection. So at first glance, it might look safe, it might look logical, but it isn't. Okay, so let's run it and see why it's definitely not the way we would want to run this. So similar to the last example, we've got a for loop, we've got 20 tasks this time, and we're going to loop through each of those. We're going to iterate up to 20. We're going to spawn a new task on each iteration, and we're going to say if the orders contains the specific order ID, so at the moment that's just going to be I, then we'll wait 10 and then we'll add that order in. So let's run that. And you can see total orders is 18. So notice the count on that, 18. Let's see if that's the same next time. 16, 19. It's not consistent. So that's a real worry. It's 19 again, but you know that it's not always 19. We are actually hitting 19 at the same time this time. Okay, 17. So every so often we're slightly out. That's obviously an issue. So why is this happening then? Well, this is happening because the check, so this checking if the order contains that order ID, and the add are two separate operations. The two threads can both see the item is not present and then both add to it. It's a classic check, then act race. So we can fix this in the same way we did in the previous example. We can protect the entire operation with a lock. So just like before, I'm going to add a private static read-only object. We'll call it _lock and new that up. And then this logic that we're actually going to do needs to be locked. It needs to sit inside that lock. So before we do the check, we'll do lock, use that lock object, and then I'll take this if statement with the logic inside it and put it inside the lock. So now the check and the add happen together as one protected action. So let's run that again, and that's giving us 20. So actually the correct answer is 20. I was seeing 19 quite consistently. But if we run it again, just to make sure that everything is definitely 20 every time. Yeah, we've got 20 there, 20 again. It's stable, it's consistent, it's correct every time. And that is the real important thing. That's what you're trying to achieve. Is if you're using all these different tasks, that's great, but it's got to be synchronized. Now, locks are great. They're a really handy piece of functionality in .NET, but alternatively, potentially a better practice would be to use an alternate data structure. And in this case, we could actually use a concurrent collection. Concurrent collections are great because they handle synchronization internally. So we can get rid of this lock functionality here, get rid of the lock object because we don't need it anymore. And then we can change the orders here from just a static list of integer. And we can change this to a concurrent dictionary. It's a concurrent dictionary of T, key, T value. So you can add generic data types for your key and your value. So we could say that we're going to use an integer for the key, and then you're going to use something like, let's say, a byte for your orders. It could be that you put bytes in there so that you can serialize those and then deserialize them back to something elsewhere. That's fine. But the key thing there is that this concurrent dictionary is already set up for thread safety. It's already set up to avoid those race conditions. This is now showing as red because it's not going to work, and that's because we don't actually need to check to see if it's already contained within the orders collection. So now we can get rid of this, and instead we can just say inside the task we're going to say orders dot try add. So try add will attempt to add the value in, and obviously if it already exists, then it won't add it. Add order ID, and then I'll just put 0 bytes in there. And then we're still waiting for all the tasks to be completed, and then we're going to look at the total order count and print that out to the console. So let's just click start, and let's see if we get the same result. We get 20. Again, I'm just going to run it again, and then one more time just to demonstrate that consistency. So we've got less code there. We're not having to do if this already contains this, blah, 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 doing a lock. We can just say use the right collection, concurrent dictionary. .NET is designed to have these thread-safe collections in these scenarios, and then we can just say try add. So I think the big takeaway is this. Race conditions don't happen because threads are evil. They happen when shared state meets non-atomic operations without coordination. So if your code reads something, if it makes a decision, if it writes something across threads, you should be immediately suspicious. You need to protect that critical logic. Use your atomic operations when appropriate. These operations which are complete, they happen beginning to end, or they don't happen at all. And never trust the timing to save you, because timing is exactly what breaks in this kind of scenario. So I hope you enjoyed this breakdown of race conditions in C# and how to fix them. If you did, you can subscribe for more practical .NET content where we explore the bugs that don't show up until production. And those are always the fun ones, right? See you next time.